Okay, so we will start now.
Yes, sir.
Yeah. So this is live session 7, right? So what we will do in this session, this will be more of a theoretical session, uh, more of a metallurgical discussions, whatever we will do today. So we'll go through one by one. So first we will discuss on residual stress. I will try to keep things brief. So first we will discuss on residual stress. Then next we will be talking on basic basic solidification concepts. Next we'll be talking on solidification cracking, and if time permits, we will be also talking on for transformation hardening. Okay, so we'll go through this one by one, four topics. So what is residual stress? What is residual stress? Residual stress is a kind of stress that will exist in your body or the component what you are uh, developing. If you are not applying any external load, the stress whatever will remain inside your object, that is my residual stress, right? So sometimes it is also called as internal stress. So residual stress is also called internal stress, right? Now, how does it develop? So for that, I want to use some analogy. So I want to use some analogy of something called uh, that will be better to understand if I provide that analogy and you can compare it with your welding thing. So I will use some analogy of something called three bar arrangement. So in three bar arrangement, let's say you have two constraints like this, and you have three bars which is connected to these two rigid bodies. So these are fixed in nature. Okay. So these are fixed in nature. Now, in this figure, these bars, 1, 2, and 3, they are identical in geometry, identical in material property. Okay. And they all are kept at room temperature initially. So temperature initial, material property, geometry, all are identical. Correct? So these are my assumption in this analogy. Now let's say the middle bar alone is heated up. So I'm heating up this material, the bar number 2. What will happen if you heat up this material? It will try to expand because of its thermal expansion coefficient. And if it is trying to expand because of its expansion coefficient, what will happen? That will be restrained by your sidebars, right? So consequently, a compressive stress will be developed over here. So during heating, bar number 2 will be having compressive stress. Agreed?
Yes, sir.
Okay. And the tendency of developing this compressive stress, they will increase with increase in temperature until your yield stress in compression will be reaching, right? So this compressive stress will be less than equal to sigma yield in compression. That's what I am telling, right? Now, basically, this yield stress will be representing the upper limit of the stress in a material, right? If any plastic deformation is occurring, so my yield stress will tell me what is the upper limit of your stress that can generate when you are hitting, only because of uh, temperature change. I'm not I'm not applying any external load, right? So it's all thermal stress, whatever is getting generated. And when you will stop your heating, what will happen? The middle bar will be allowed to cool off, right? And its thermal contraction will be then retained by the sidebars. And that compressive stress, what was generating during your heating in the middle bar, that will drop rapidly and it will change to tensile stress. So during cooling, my bar number 2 will be having a tensile residual stress, right? So this analogy is similar to welding. In the weld metal and the adjacent base metal, these are analogous to the middle bar, whatever I am talking now. And the areas far away from the weld metal that are analogous to the two side bars. So in weld metal, if this is your plate and you are joining something like this weld metal is your middle bar and this region, the far away from that weld metal are those side bars, right? So because of expansion and contraction of your weld metal and your adjacent base metal, which are restrained by the areas away from your weld metal, because of those things, at the weld region, you will have tensile stress, and far away from the weld region, you will have compressive stress. As simple as that. Now, uh, I have to draw another schematic representation. So, so I will draw somewhere here. Then. So let's say this is a semi-infinite domain. Okay, and I'm welding over here. This is the line where I will be traveling my heat source. So over here, the melting has started, and this is my hatch region where the welding will take place. right? So this hatch region, what I am talking about, over here, there will be plastic deformation because of thermal stress. This section, let's say there is a section I am taking AA, which is ahead of your heat source. So my heat source is starting from this blue region. Heat source starts from here. Now, will there be any effect on section AA on your stress that will be getting generated if it is ahead of your heat source? Of course, that will not significantly be affected by the heat input, right? So, due to temperature change during welding, my residual stress will be essentially zero at section AA. Now, let's say I am making a section at this region BB. So, this is intersecting my heat source. One section I am taking along section CC at some distance behind the heat source. So, let's say this is section CC, and far away this is section DD. So how my residual stresses will be getting generated at those sections? Of course, at AA there will be no zero residual stress. Sigma x is zero over there. Let me add. So sigma x will be zero at section AA. Now at section BB, my sigma x is close to zero in the region underneath the heat source. Why? Because the weld pool doesn't have any strength to support any loads, right? So in the region somewhat away from your heat source, stresses will be compressive because expansion of those areas will be restrained by your surrounding metals, which are at lower temperature. So at section BB, I will draw, let me remove this. So at section BB, my stress will be something like this. So the black is tensile, and over here, these white portions are compressive. Now, as we go away from those melt region, you will there will be tendency to increase your tensile residual stress in the center of your weld line. So at section CC, it will be something like this. So the black hatched line is my tensile residual stress, and at section DD, this will be more tensile residual stress will be getting generated over here, right? Confusion.
No, sir.
So what will happen because of residual stress? Why residual stress is important to study in welding? So because of solidification, shrinkage and contraction, whatever is happening in weld metal during welding, the workpiece will have tendency to distort, right? So residual stress and distortion are interlinked. Residual stress and distortion are interlinked. There are several types of weld distortion. I will not come to that. So basically, you have some transverse shrinkage, you will have some angular distortion in different weld design. Like you can have angular distortion in butt weld, you can have angular distortion in your fillet weld, there can have some longitudinal shrinkage in your butt weld. So there are different kinds of distortion based on different residual stress that is getting generated. Now, what are the remedies? So how can you try to reduce this residual stress? So the remedies to reduce residual stress. What can you do? Any suggestion? What things we can do? Of course, we can do some heat treatment, right? So we can do some
Pre preheating or post heating, both.
so we can do preheating or post heating
Yes.
to reduce your
Tensile residual stresses will decrease.
post and preheating. Anything else? Can do something called stress relief annealing. Everything is depending on your how much time you are heating up. So soaking time is important in your heat treatment method, right? So in stress relief annealing, basically you're heating up metal to a specific temperature below its melting point. You'll be holding that for a period of time, followed by some slow amount of cooling. So what will it do? It will allow your atoms to rearrange and relax your internal stresses if it is anything there. In terms of mechanical methods, these are let's say thermal classification, right? Thermal methods, those heat treatment methods. Any name, uh, any mechanical methods through which you can do reduction of residual stress. Just a minute.
Thermal coefficient of expansion, we can, if we will decrease, it will lead to decrease in residual stresses.
Come again?
Alpha coefficient of thermal expansion.
Mm-hmm.
If we will decrease it, then it can leads to decrease in residual stresses.
So, I mean, that is a material property,
Yes, yes, material.
right? That is a material property. So,
You are asking about
what can be a mechanical methods to reduce your residual stress? So, heat treatment is a thermal method. The stress relief annealing, post welding, preheating, post welding, not post welding, post weld heat treatment, preheating, tempering. So, these are some thermal methods through which you can reduce residual stress. What can be some mechanical method? So, you must have heard of short pinning.
yes, yes, yes. Short pinning was yes,
So, you have
yes,
heard of short pinning. So, what
yes,
is
yes.
short pinning?
उसमें बॉल्स वगैरह जो होती है हिट करते हैं
So short pinning is basically you will bombard your material surface with some small spherical media. So there
Yes.
will be some balls, steel
Yes.
balls
Yes.
possibly, through which you can provide some impact on your metal surface that will generate compressive residual stress. So if some kind of tensile residual stress is there, that will get suppressed. If any crack tendency is there, that will get suppressed because of short pinning. Then you can have some surface rolling. So basically you have to deform the metal. Compressive deformation, of course. So these are some mechanical methods. You can also do cold working. It is the most viable option, cold working. That also can reduce your residual stress.
Welding sequence.
Yes, welding sequence is a uh, part of your heat treatment thing, actually. I mean, when you will change your, so let's say you are doing some laser welding or you are doing some arc welding, you can do some pulsed thing,
Yeah.
pulsating. So in that sense, yes, it will reduce in some sense the residual stress. We have something called laser pinning also. Through laser also you can pin the material. So we will use some high intensity laser pulses to create shock wave. So this is also a method. High intensity laser pulse to create shock wave. Okay, so let's see if any question is there from residual stress. If not there, then we'll go to solidification solidification part. Uh, yeah. So can you answer me question 5?
Away from fusion,
After,
I think negative compressive stresses.
So become more
af-
compressive in nature with
Away from the distance.
increase in distance from the fusion zone.
Yes.
After nature.
Option A. Correct. Anything else? Anything else? Anything else? Okay. So we'll move to the solidification part now. So there are a lot to tell in solidification concepts, but because of time constraints, I will stick to some. Um, I'll stick to few things. It's not possible to tell everything. Anyhow, so in solidification concept, there is something called equilibrium partition ratio. Equilibrium partition ratio. What is equilibrium partition ratio? So it tells me at any temperature T, let's say you have some temperature T, the equilibrium partition ratio is defined as Cs by Cl. What is Cs? What is Cl? Cs is my composition of the solid and Cl is my composition of the liquid. So if you are having some solid liquid interface, when it is getting solidified, Cs is my composition of solid, and this is composition of liquid, right? So what are what is the what is the main parameter upon which K will depend? This equilibrium partition ratio will depend. This will be greatly dependent on the temperature, right? The temperature will change your composition. Enough. Okay. So um, how should I move? So let's take one example. Let's take one example of a part of a phase diagram. So for simplicity, what I will do, K will be assuming as constant. If I am assuming K as constant, that means the solidus and liquidus line are both assumed as straight lines. So let's say this is my solidus line, and this is what this is liquidus line. You are aware of this terms, right? Solidus, liquidus in phase diagram. So I'm assuming K is constant, so that will be a straight line. Now, let's say my melt of initial composition is at constant. What is x-axis and what is y-axis? So y-axis temperature, x-axis
X-axis carbon composition.
not carbon composition. So carbon composition is for iron carbon. So if I am
Okay, okay.
making some generalized point, this is composition or solute concentration, right? Now let's say my the male component is initially having a composition of C naught. It is something over here, something over here. This is having composition C naught. So the first solid it will form, the first solid it will form. What will be the first solid it will form? The composition over here. This is my liquidus line. This is my solidus line. So at this region, liquid and solid will coexist, right? This hatched line. Correct. Agreed, right? So what will be the composition? The first solid it will form. What will be the composition? So I have defined equilibrium partition ratio as K, and my initial composition is C naught. So this will having a composition of Kc naught, right? According to this equation, right now. So I'm basically telling that Cl is equal to C naught at T equal to TL. So this is my temperature TL, and This is my temperature Ts. So the range, freezing range is from TL to Ts. This is my, I would say, equilibrium solidification range or equilibrium freezing range. Right? So this concept is for k less than 1. There are some other concepts where k will be greater than 1 and some other things. I will stick to a single concept to give you some glimpse of what happens as a concept of equilibrium partition ratio. So basically over here it says that the solid what it will form that cannot accommodate as much solid as the liquid does. Because k is less than 1, the slope is negative. This will tell you this will tell you so this is continuation of this, huh? So this will tell you solid can't accommodate the solute as much as the liquid does. What does that mean? What does that mean? So basically your solute, the solid that will be rejecting your solute material into the liquid during solidification, right? And because it will reject the solute material during the solidification, the solute content of the liquid that will continues to rise during the solidification, right? So solute content in liquid metal continues to rise during solidification. How will it look like if k is greater than 1? So when k will be greater than 1, the solute content of the liquid that will continues to drop during solidification. So if k is greater than 1, it will look something like this. So this will be my liquidus line and this will be my solidus line. That will be a reverse. This is for k greater than 1. Most of your phase diagram, you will see that k is what? Less than or greater than? So for most of the cases during solidification, solute will be getting rejected, right? During solidification, the concentration of solute will get increased with time during solidification, right? Difficult to grasp or something as you are able to grasp something from this discussion. Any response? No response. So I think this is going to a little bit difficult, right?
Yes, sir.
Yeah. Okay, fine. So stick with me. So next I will talk about some solidification modes. So during solidification of a pure metal, solid liquid interface is usually planar unless you are doing uh, some kind of undercooling is imposed. The solid liquid interface will be planar. But uh, during solidification of an alloy, they will have different modes of solidification. What are different modes of solidification you have come across? This I have just talked, planar. What else? You can have something called cellular structure. You can have something called
Dendritic,
dendritic.
equiaxed,
You can have equiaxed dendritic. So that will depend on your solidification condition or the material system that is getting involved. Right? Now, now, uh, fine, fine. So I'll directly come to the condition. I'll directly come to the condition. So I was talking about equilibrium freezing range, right? What is that? What is equilibrium freezing range? Is TL minus TS. This. So from a equilibrium phase diagram, you can find out what is my equilibrium freezing range, right? Now at steady state, at steady state, thickness of boundary layer at solid liquid interface. So boundary layer means, let's say this is over here, you have some melt composition. Let's say this is solid, this is liquid, and you'll have some interface where both will coexist. So I'm talking about at steady state, what is the thickness of this T? So T is defined as dl by R. What is dl? dl is diffusion coefficient in liquid. What is R? R is solidification rate. Okay. Okay. Now I should have drawn the composition diagram, then it would be much. I will not say that will be easier, but at least that will be for better understanding. But fine. So the composition diagram will be something looking like this. So this is my distance from solid liquid interface, and This is composition. This will be something looking like this. One will be at C naught, one will be at C naught by K. What will be the slope? The slope is defined as the tangent basically.
Yes, yes. So dy by dx.
Yes. So this is defined as delta T, which is the temperature difference, that
Dy.
divided by this thickness.
Yes.
Right? Now, for a planar interface to be stable at steady state, what criteria you must meet? G by R, that should be greater than delta T by dL. What is G? Over here, G is my actual temperature gradient. R is solidification rate. Delta T is equilibrium freezing range, and dL is diffusion coefficient in liquid. So just remember this criteria which need to be made if you want to have some planar interface in your solid liquid interface. But in real scenario, you'll never have some kind of planar interface. Enough. So you'll either have some columnar structure, or have some equiax structure. So those things are there. Now, if we concentrate on this equation, G by R is greater than equal to delta T by dL. What can we infer from this equation? So it will tell me, I will note it down. It will tell me few things. I'll note it down. So if your temperature gradient is higher and your growth rate is lower, what will happen? If your temperature gradient is higher and growth rate is lower, it will be easier for a planar interface to be stable, right? Easier for planar interface to be stable. Now let's say you have some freezing range, delta T. It is very high. So the difference between TL and TS, and diffusion coefficient is very low. What will happen? For a planar interface to be stable, this condition will be better, or this will worsen your planar interface to be stable. So if delta T is getting higher and DL is getting lower, this value is be getting higher and higher. This is not easier for a planar interface to be stable at this condition. Right now, just concentrate on this condition. So this is more difficult for planar interface to be stable. At least from this slide, do you have any question? Let's say you know this condition to have some planar interface, that is G by R is greater than equal to delta T by BL. Now I have made some conditions, I have made some comments on what should be higher, what should be lower to have the planar interface in your structure. Is this understood? This slide.
Yes, yes.
Great. So next I will talk about this. I will talk about this different modes of solidification. What we are talking about. So I'll basically draw a diagram. So I will refer a diagram what is that is very famous. So let's say in this direction I will be increasing my supercooling or the undercooling. You will tell me what is undercooling. We are talking about this again and again. Undercooling. What is undercooling? Or what is the definition of undercooling? Hmm? So let's take this slide. What is undercooling? So
Cooling a
undercooling.
liquid,
Yeah, tell.
cooling a liquid below its freezing point without solidification.
Right. So if you are cooling below its freezing point without any phase change
Phase change.
or something like you are telling that from liquid to solid, that is phase change. So material will remain in its liquid state even though you have cooled it below its freezing temperature, right? So liquid is cool below its normal freezing point without any phase change. What factors can influence undercooling? The first and foremost thing is cooling rate. If you're cooling it very fast, faster cooling will lead to a high degree of undercooling because there will be less time for nucleation to occur, right? So cooling rate is one parameter. Uh, Purity of metal also influence a bit on your undercooling aspect. So if there is impurity in your liquid, that can act as nucleation sites. That happens in an alloy system in your if you are welding dissimilar metals, that will happen. So you are making alloy, you are allowing impurities to uh, impurities will be there. Impurities in the sense there will be those solute concentrations, right? They will acting as a nucleation sites, and that will make harder to achieve undercooling. So undercooling, that will decrease if your impurity is higher. Undercooling will let me write it down. Undercooling will increase if your cooling rate is increase or decrease. Cooling rate is also increased. So I was talking about this, where you will have uh, where you will have some. So let's say this is your equilibrium, and this is my actual. There is no undercooling. It will give me some planar. So this is equilibrium. This is actual. If you have some amount of undercooling, you'll have some structure like this. What is this structure? Cellular. If you have some more undercooling, we will have some structure like what is this kind of structure? This is columnar dendritic. And finally, if you have the undercooling is much more. This is sorry. So this is my actual. This is more. We'll finally, but we'll get this is
Planar.
equates dendritic. So you'll have something like this. This is okay. Can you tell me the region where dendrites, both columnar or equiax, and the liquid phase that will coexist, what does it known as? It is known as something called mushy zone, where liquid and solid will coexist. So at a very high degree of supercooling or undercooling, whatever you will tell it, the mushy zone can become so wide that it is easier for aqueous dendrites to nucleate than for columnar dendrites to stretch all the way across those mushy zone, right? So you are widening this TL minus TS thing, and you are widening this supercooling thing, there will be more tendency to form equiaxed dendritic structure rather than stretching it as a columnar kind of structure. There are different theories to explain this in a analytical or semi-empirical or empirical form. Yeah, fine. So is this good enough? So there are another figure actually. Uh, there is another figure that also is referred as a base or very known figure in solidification concept. Uh, should I draw it? Should I draw it? Yeah, fine. We have some time. Let's draw that figure. So that will tell you, or you can take it as a reference in terms of this temperature gradient solidification rate thing with your, you can relate it with your microstructure. So we'll try to draw it in a cleaner way. This is R. What is R?
Solidification rate.
So R is solidification rate or growth rate, and G
Actual temperature.
temperature, right? So basically G by R will determine the morphology of your solidification structure, and G into R will determine the size of your solidification structure. So G by R will tell you the morphology, G into R will tell you the size of the morphology. So I'll close it down and give me some time, okay? So over here, so this region in the left side, you will have high G by R, right? So at the topmost region, you will have the maximum temperature gradient and lowest solidification rate. So this region is high G by R ratio. And let's say this region is low G by R ratio. Now, this curve, this left curve This represents lower cooling rate. So G into R, that is lower, that will give me coarse microstructure, and this one will give me higher cooling rate with fine microstructure. Right? More you going towards right, G into R value is going to be higher. More temperature gradient, more growth rate. Now, this is planar. I will take some different color. This is cellular. This is columnar dendrite, and the final structure you have is different color. Let's take green. This is equiaxed dendrite. Okay. So this figure, you must remember this figure to to have the idea of what should be my solidification rate, what should be my temperature gradient, to have some different microstructure. To you should have some idea at an instant that if my temperature gradient is higher, solidification rate is lower, what should be my microstructure? It will be finer, it will be coarser, it will be columnar, or it should be planar, or what it will be. So you always refer this figure. So this is, you must take it as a reference figure. So, to get idea of solidification. Okay, so let's quickly go through some questions. Let's quickly try to figure out uh, what are some related questions of what discussions we have till now. The first one is itself related. Equiaxed grain structure is the result of solidification at. So when I am talking about equiaxed, you must have think it of as equiaxed dendritic.
Low growth rate and low temperature gradient.
So it is telling me if my growth rate is higher towards this and my temperature gradient is lower, it will have more tendency to have equiax dendritic. Do you agree?
Yes, sir.
So low temperature gradient and high growth rate. D. Next. For a planar interface to be stable at S by L interface, so this we call it SL interface. At SL interface, so following criteria that need to be met. This we have discussed. These two, right? Agreed, right? I'm moving them.
Yes, sir.
Next, with increase in degree of supercooling tendency to form columnar structure, of course, this will be increasing. So, uh, again, so I must have mentioned it as equiaxed columnar. That will be more suitable. So, with increase of degree of supercooling, tendency to form equiaxed columnar structure will increase. Then, with increase in cooling rate, the solidification structure become,
Finer.
of course, this will be final. Question 5 is done. Okay, okay. Then we will move to this. Next, we will move to this solidification cracking, and if time permits, we'll have some discussion on this phase phase changes in iron carbon phase diagram, right? Uh, but you are more familiar with, of course, iron carbon phase diagram. So that's why I have kept solidification cracking discussion initially, and then I will try to finish that with this change in phases during heat treatment in your iron in your steel metals. So next we will be talking on this cracking concept. Again, there are a lot of things. Have to keep it brief. I need to keep it brief. So if you see solidification cracking now, so where can you see solidification cracking? Wherever there will be this phase change, melting and solidification, right? So you can observe that in castings, in ingots, right? And also in fusion welding, of course. And these kind of cracking are intergranular in nature. What is intergranular? The cracks will form along the grain boundaries of the weld metal during the terminal stage. I mean, it will not form at the initial stage of solidification. That will form in the final stage of solidification when there will be tensile stresses will be generated, tensile residual stresses will be generated at you. center of weld metal. You know? So solidifying weld metal will tend to contract, as I was talking. We try to contract because of solidification, shrinkage, and thermal contraction. And what will happen to surrounding base metal then? They will also try to contract, but not as much as the weld metal is trying to, right? Because it is neither melted nor heated as much on the average compared to your weld metal, right? So yeah, so mm, tensile stress, tensile residual stress in center of weld and compressive residual stress away from weld. This is known. This we have already discussed. Now, give me some time. I'm just taking time to find out what I should talk about, what I should talk about to make it more brief or that will be more effective for the short time period of discussion. So, if we talk about solidification cracking, we always try to understand uh, what should be the factors that is uh, that is enhancing that tendency to have that cracking, right? So we can discuss on the metallurgical factors that will give me solidification cracking. What are those?
Impurities.
Yeah. After
If we will increase the impurities, it will lead
you
to.
are not you are not audible.
If we will increase impurities, then it will leads to or promote solidification cracking,
Mm, mm.
and
So yeah.
because melting point will decrease and solidification increase, so this will promotes the solidification cracking.
Okay. We'll go one by one. Uh, of course, one is solidification temperature range. One is solidification temperature range. So generally speaking, wider the solidification temperature range, larger will be that mushy region in your weld metal, right? And larger the area that will be weak and susceptible to solidification cracking. So if this is increasing, cracking tendency will get increased. So people do some alloying to uh, reduce your temperature range. So solidification temperature range of an alloy that will increase as a result of either presence of some impurities. So there are some impurities as sulfur, phosphorus in steel or nickel based alloys. They will always increase your solidification temperature range, sulfur and phosphorus in steel, right? So yeah, those kind of impurities are always provide you severe cracking in carbon steel or low alloy steel, even at low concentrations, they have a strong tendency to segregate basically. They have a strong tendency to segregate at grain brown juice and to form some low melting low melting point compounds. So you can have some compounds like iron sulfide, iron phosphide. So those are low melting point compounds, and that will have some tendency to segregate at the grain boundaries, that will weaken the grains, and they will have some tendency to crack. Now, in solidification range means yeah, that is one factor in that is solidification temperature range. If you have some eutectic reaction, so that will also happen, right, during terminal stage of solidification. You'll always have some eutectic reaction. I have shown you what is eutectic. If there is eutectic reaction taking place, that will also extend the solidification temperature range. So those are mostly common in aluminum alloys. So this is one, sulfur and phosphorus. Eutectic reaction also will increase your temperature range. That is one. That will also increase your solidification cracking thing. And next, next we can talk about this amount of liquid, amount and distribution of liquid during solidification. You know, so basically in terms of this is already shown. This is already observed in aluminum alloys that let's say you are mixing up copper. If you are increasing copper percentage, and let's say this is my crack sensitivity or crack tendency, it will follow some distribution like this. At maximum composition percentage, what will happen? If any crack is happening, it will heal by the liquid metal, and there is some intermediate composition where the crack sensitivity will be highest. So this will be something like this. You can also calculate the fraction of liquid through some equation. Those, let's keep that. Then then I can talk about this ductility of the well metal. So less ductile a solidifying weld metal, what will be for crack tendency? If it is less ductile, crack tendency will be much higher, right? So it will crack during solidification. There are something called ductility test curve that also I will not cover. And finally, I can talk about surface tension. Surface tension of grain boundary liquid. So higher the surface tension of the grain boundary liquid, there are some concept of dihedral angle. So Let me draw three separate figures. One is something like this. One is something like this. And one is something like this. So let's say dihedral angle is theta. Theta is lowest for case 3, right? And highest for case 1. So this is my dihedral angle, the angle between these two. And this portion is my liquid. This portion. This portion is the liquid, and these are the grain boundaries over here. This is the liquid portion. So theta 1 is higher than theta 2 is, and theta 3. Right? So if your surface tension is higher, if my surface tension is higher, what will be for dihedral angle if surface tension is higher? If the surface tension is higher from those grain boundaries, what your common sense is telling me. Dihedral angle will also be higher. Okay? So surface tension higher, larger the dihedral angle. Now, how will it affect your crack sensitivity? People have shown that these are all experimental results, of course, based on lot of researches. So if you are increasing theta, and this is my crack tendency, with increasing theta, my crack tendency will go down. Right? So crack susceptibility ability increases with increasing dihedral angle. If the surface tension between solid grains and the grain boundary liquid is very low, what will happen? So liquid film will form between those grains, and uh, yeah, so that will increase your cracking susceptibility. So if your surface tension is very low, crack tendency will be higher. One more is there is another factor. So this is 1, this is 2, this is 3, 4. There is another factor. It's grain structure of, sorry, grain structure. So fine aqueous structures, are they more susceptible or less tendency to cracking?
Less tendency, sir.
So they will have less cracking tendency. Compared to the coarser one. So fine aqueous grains, those can deform to accommodate contraction strengths more easily. During solidification, you will have contraction strain, right? So fine or refined microstructure, they can deform to accommodate those kind of strains more easily. They are more ductile than the columnar grains. I was talking about this also. This in situ healing of in situ healing of crack. So basically, liquid will be feeding and healing if there is any crack. That can also be a more effective in fine grain materials, right? Any idea of what is liquefaction cracking? This is solidification cracking based on this thermal contraction and those things. What is liquefaction cracking? This is also called hot cracking also, So write it down. Is something called liquefaction cracking. So if you have presence of low melting phases at grain boundaries that liquefy during heating, and that will result upon cooling. So uh, so the mechanism is something like this. It will mainly happens in it will mainly happens in it mainly happens in partially melted region. Yeah. So in partially melted region. So let's say uh, you have some region something like this. This is my fusion zone and this is my partially melt region and this is the base metal. Okay. This is my base metal. This is partially melt zone. This is fusion zone. So liquefaction cracks typically form during cooling stage when the solidifying grains begin to pull apart. So if you have some, let's say faster cooling, so these part is also trying to contract this base metal and you will have partial liquefaction over there. So let's say you have some grains, something like this. And during contraction, if they are trying to pull it apart, there will be in between liquids which will still not be solidified, and some part will be solidified, which will be apart, right? Because of those tensile stresses caused by some thermal contraction. So yeah, this is called equation cracking. So mainly this appear at grain boundaries where liquid films will be present, because grain boundaries cannot resist the contraction force, and the liquid film, they do not solidify quickly enough to offer strength, right? So yeah, that is there. Yeah. Any question?
Sir, cold cracking a belt joint cannot be minimized using. कोल्ड क्रैकिंग बेल्ट जॉइंट में हम कौन कौन से पैरामीटर्स हैं जिससे मिनिमाइज नहीं कर सकते? लाइक प्रीहीट ऑफ द बेल्ट मेटल, it can be used to minimize the cracking tendency. Filler metal of high yield strength. Post weld heat treatment also reduce the cold cracking tendency, reducing tensile residual stress. This is a objective type questions. Cold cracking of weld joint cannot be minimized.
So can you come again with the options?
Option first, preheat of the weld metal. Option second, filler metal of high yield strength. Option C, post weld heat treatment. And option D is reducing tensile residual stress.
So the second one.
Filler metal of high yield strength.
Yes. So
Oh,
both preheat and post heat, that can reduce. If you are reducing your tensile residual stress, of course, that cracking tendency will get removed. There is nothing as such on filler aspect. So for me, the second one is the correct one, which will not
yes, sir.
affect.
Two option A and C is to decrease cracking tendency, but option B and D में doubt था.
I mean, if you can somehow reduce your tensile residual stress, that means you are
Yes, sir.
generating some compressive nature in your residual stress. I was talking about the short pinning thing or heat treatment thing, right?
Okay,
So
sir.
if you can somehow reduce your tensile residual stress, this is also a post processing. Whatever we talk about this pinning thing, na short pinning, leisure shock pinning in terms of mechanical, and then you have those stress relief annealing. Those all are post processing after welding is done. So if you can somehow reduce your tensile residual stress, of course, that cracking tendency will get reduced.
Okay, sir. Sir, one another question.
Yeah.
The chance of solidification cracking will be minimum if
Okay.
the weld joint of composition is eutectic alloy, hypoeutectic alloy, hypereutectic alloy, all of the above.
So if you're just again tell me the
The
question.
the chance of solidification cracking will be minimum if the weld joint of composition is option A eutectic, option B hypoeutectic alloy, option C hypereutectic alloy, option D all of the above.
So this is little bit tricky for me. This is little bit tricky for me. So
I
eutect,
think hypoeutectic alloy contain ferrite phase and ferrite is a soft and ductile.
yes.
So maybe hypoeutectic eutectic Li
Yeah.
cracking will be
So
minimum.
there is no confusion with hypo
Yes, sir.
because the concentration of the impurities is minimal over there. If you go towards eutectic, the tendency will get higher. But you see, this figure, this has been done for aluminum alloys. It is not that more you are increasing copper, there should be tendency of cracking also is getting increased. So there is some intermediate copper concentration where I have the maximum cracking tendency, and after that again this is getting reduced because of uh, the feeding of that filler metal. Means if you have some more copper concentration, the the flowability of the melt will be much better, and if there is any crack formation is there, that will heal that crack. So uh, yeah, for me, the list tendency, yes, of it will have the hypo thing, as you are saying, it will have ferrite, and more you are going towards hyper thing, more you are going towards hyper eutectic. Uh, if we are thinking in terms of iron carbon phase diagram, uh, there will be these cementyl phases, right? So
Yes, sir.
there will be
Carbon contain more than
carbon content will
0.8%.
get higher.
Yes,
So
sir.
cementyl phases will be forming at those grain boundaries. Those are brittle in nature. Then they can increase your cracking tendency. Yes,
And cementite is a hard and brittle.
right, right, true. So yeah, why don't we directly? So because I have some, I have provided least importance on this iron carbon phase diagram because this is the mother phase diagram what we have all known of, right? So we have learned things from iron carbon phase diagram only. So that must be known to all of you guys. So that's why I have kept less importance on this iron carbon phase diagram. But let's have these question and answers from this iron carbon phase diagram thing. Ah, this I was talking right now. As the carbon content increases beyond 0.8%, tensile strength of plain carbon steel starts to decrease due to the cementine formation. Agreed or not?
Yes, sir. But sir, इसमें higher carbon percentage increase the strength and hardness of the material. But here plain carbon steel
I'm talking
start
about tensile
decrease.
strength.
Okay, sir.
So yes, hardness will increase, but if you means any kind of brittle material, you see the hardness will be higher. But if you are having some tensile nature, it will fracture immediately. है ना?
Yes, sir.
Next, austenite is transformed to something when it is rapidly cooled or quenched. So this is something on you have. go on through your CCT diagram or TTT diagram. So this will give me metastable martensite formation. Then choose the correct statement from the following about solidification cracking. This doesn't happen during initial stage of solidification, so this is not true. This is true. Fine grains promote cracking tendency. No. Compressive residual stress promotes solidification cracking. No. So B is correct option. Agreed?
Yes, sir.
This question was from the previous discussion anyhow. You remember we talked about this shape of the male pool. So where is any? Do we have any? We have some. So in terms of shape of the male pool, if you shape of male pool, so I'm diverting a little bit from today's discussion. Anyhow, so there can be some circular shape, then you have some elliptical shape, then you have some more elongated shape like this. So this will be more white enough, and this will be more elongated. Do you remember this discussion from the previous lecture? So from there, uh, this question was about elongated and tear down shape of the weld pool for same heat input is formed at
High welding
high
speed.
welding speed. Correct. Phase in stainless steel which promotes cracking is ferrite, ferrite, or ductile enough. What is ledeburite?
Lead burite is a mixture of austenite and cementite, I think.
This is mixture of austenite and cement. So the phase in stainless steel which promotes solidification cracking is uh, austenite actually.
Sir, one question also doubt.
Yeah.
It is a objective type question. In case of similar metal fusion, welding of weld metal solidifications occur by option A nucleation and growth, option B growth only, epitaxial only, and option D is columnar grain growth. In case of similar metal fusion, welding of weld metal solidifications occur by
So if you are doing similar welding, we can remove nucleation. So if there is no alloying element, there will be no segregation. So there will be no nucleation site. So the mechanism is not nucleation. Okay, that is not true. Next,
growth. I think growth only.
one was that growth.
Yes, sir. Second is growth only. Third is epitaxial only. And option D is columnar grain growth.
So In columnar grain growth, one is columnar grain growth, one is grain growth, one is epitaxial grain growth.
Yes, sir.
Grain growth must be there. Why not columnar grain growth? Means in similar metal structures, we have seen that there are columnar grain structures formed. Do you know what is the correct option? I mean, from where these questions are coming?
Okay, sir.
No, I mean, from where you are giving me these questions? That's what I am.
Assignment, it is from assignment which is given on
So
NPTEL.
these are assignment questions.
Yes, yes.
So when you will get to know about the answers? Next week or when? I don't know.
Okay, sir.
No, I'm asking कब मिलेगा आंसर इस क्वेश्चंस का राइट आंसर क्या है वो
Sir,
कब पता चलेगा
I watched video of a cracking solidifications. So, as per the video of sir, growth only is a correct answer of this question.
Sir, the answer will be available after 11 September.
सर 11 September
Yes,
that
yes.
is after tomorrow
Yeah,
day,
day
day
after.
after tomorrow
Yeah, yeah, yeah.
okay
Because deadline is 11 September and midnight. Up to midnight, we need to submit the assignment.
हम्म
So after that, the answer key will be available.
ठीक है let me know
Sir, in my opinion, the answer will be uh, in my, the answer will be C, sir.
columnar
Epitaxial.
okay
Growth and most probably the answer is epitaxial because I'm in my opinion, sir. C. The answer is C.
and why
Why?
hmm. That's
Because
what I was thinking means
in case of similar metal fusion
yeah
welding,
so you are stating that in case of similar uh,
because
similar
in dissimilar metal nucleation and growth takes place,
ha means
and solidification of weld based on
no
just
one minute so there was two options nucleation and growth were two separate options is it or
no no no
nucleation and growth it was
no nucleation and growth only option one,
ah
option second growth only.
so of course nucleation and growth I have removed that option
Yes,
I was confused about means
growth and
growth epitaxial growth and columnar growth means
sir, I think solidification of weld based on just growth is called epitaxial growth. So the most appropriate answer will be C, in my opinion.
hmm, hmm. Still not sure
Yeah, not
I
sure, but
have to check once
because
means I have to think also it
two
seems
words
for
are
me it seems like either columnar or epitaxial means columnar also happen in means if you see in but this is similar metal welding but yeah means in casting there is columnar structures in additive manufacturing, there are columnar structures. Why don't columnar solidification?
Sir, I think solidification mechanism are of two type, nucleation and growth, and second one is growth slip.
What is the second one?
Growth slip.
What is growth sleep?
Sir, growth slip, the partially melted grains of base metal consume the liquid metal or partially melted grain directly. So growth takes place.
I'm getting it.
The partially melted grains of base metal
Mm-hmm.
consume, consumes the liquid metal.
Okay. I have not come across this term growth sleep, but
Growth
fine.
takes
I
growth
will check
takes
that.
sir, growth takes place, but it is asking about solidification of weld based on similar material. So growth will takes place, but it is called epitaxial growth. Growth takes place, but it is known as epitaxial, I think.
Yeah, could be. Uh, I will have a look on this question. Okay, so
Sir,
I can provide some better answer in the next session in detailed answer.
Okay, sir.
So I have confusion on this epitaxial and columnar. So for me, both are true, but I need to check. Any more question?
okay, sir. Thank you, sir. Okay.
Sorry.
No question, sir.
Yeah. Okay.
Okay. Thank you.
So we can wrap up.
Yes, sir.
Thank you. Thank you.